Hello and welcome to the fourth class of the Introductory Chemistry series, where we will be talking about gas laws. So I've just sort of included this diagram because I think it shows what the essential sort of components of a gas are, and we'll get to that later. Before we start talking about gas laws, I think we need to fully understand what a gas is. So a gas is defined. Okay. So, sorry, before I go into the lesson, thanks for all of you who are watching right now, and I hope that you'll post any comments, questions, suggestions in the chat below or in the comments. Thanks for watching in advance. And please let me know if there's anything you would like to see covered in today's class, or if you have questions. Yep. Alright, so a gas is defined as a substance or matter in a state in which it will expand freely to fill the whole of a container, having no fixed shape, unlike a solid, and no fixed volume, unlike a liquid. Now that's pretty important, because a gas is basically free-floating molecules that aren't bonded to each other or attracted to each other in any way, at least ideally. Unlike a liquid or a solid, which are sort of held together by intermolecular forces, which we talked about last time. So these two dudes, Rudolf Clausius and James Clerk Maxwell, came up with a sort of theory to describe gases, and their behavior, called kinetic molecular theory. And they sort of talk about, so these sort of theory points apply to an ideal gas, or what they came up with as one. So let's just make this slightly easier to see. There are 5 components of this theory that are really important, and we're just gonna go through them really quickly right now. So a gas is composed of molecules that are separated by average distances that are much greater than the sizes of the molecules themselves. This basically means that the volume of the molecule of gas itself should be negligible, at least of an ideal gas, compared to the volume of the container. So it's basically like a point instead of a piece of matter. The second one is the molecules of an ideal gas exert no attractive forces on each other or on the walls of the container. Basically, no intermolecular interaction between the molecules of gas. The third is the molecules are in constant random motion, and as material bodies they obey Newton's laws of motion. This means that the molecules move in straight lines. Straight line random motion, basically. And the fourth one, collisions are perfectly elastic. When two molecules collide, they change their directions and kinetic energies, but the total kinetic energy is conserved. Collisions are not sticky. So the molecules do not stick to each other, they sort of bounce off each other immediately, sort of connected with the second point about no attractive forces being exerted on molecules of gases. And the fifth is that the average kinetic energy of the gas molecules is directly proportional to the absolute temperature. So the fact that it's talking about the average kinetic energy is pretty important, because actually this might be a bit too sort of, I guess, advanced for right now, but it's called a Maxwell distribution, made by the same guy who came up with the kinetic molecular theory, and it sort of talks about the distribution of speeds of molecules in a gas. Basically, you can ignore like the T1, T2s for now, and sort of just look at the curve. That's basically each point on the curve is a molecule in the gas, and you can sort of see that they're not all at the same sort of temperature. Sorry, not temperature, sorry. They're not traveling at the same speed. As you see, the x-axis is velocity. So they have like sort of different probabilities of traveling at different speeds, but the point is that some of them are slow and some of them are faster. Not all molecules are traveling at the same speed. So that's why the average kinetic energy, or since kinetic energy is related to speed, is pretty important. So why is this theory sort of important? Well, it helps us really like sort of relate the different components of a gas or properties pretty easily, or like more uniformly. But it's also important to note that actual gases differ quite widely from what this KMT, kinetic molecular theory, says about an ideal gas. So to sort of illustrate this, or not to bring an example up, let's talk about ammonia. So NH3, sort of drawn like this, with a lone pair, because this is a polar molecule, ammonia. So when you look at this sort of molecule, it's kind of big. I mean, not in the traditional sense of sort of like bigger than what our eyes can see, but like it's kind of big in terms of a gas molecule. So it definitely has volume, especially when you consider that there are different like bonds between the molecules, and these bonds are not very close together. They're not sort of like, oh, there's a straight line. No, they're kind of like clouds almost, because you're sharing electrons, and the electrons are moving like all over the place, and there's only like a general cloud where you can sort of see the limits of the molecule. So this is definitely going to have volume, which sort of violates the first point of the KMT. So if it has volume, well, what changes about it? Well, remember last time when we talked about intermolecular forces? Intermolecular forces, one IMF that every molecule has is dispersion forces, right? And dispersion forces come with the amount of electrons, or yeah, they come from the electrons in a molecule. Now, since this molecule has an abundance of electrons, it's definitely going to have dispersion forces, and that's going to sort of make the molecules stick together if they're close enough. So that kind of violates the second KMT point, which says that gases exert no attractive forces on each other. So this is definitely not an ideal gas, because of its size and the forces that these molecules these forces that these molecules exert on each other. Okay, so let's sort of go back to this diagram and talk a little bit about what some properties of gases are. So you can see here, this person has drawn in some, or labeled some different factors of a gas. So here, you can see that there's pressure, volume, temperature, and there are sort of gas molecules in a gas, obviously. And the moles of gas would be another sort of factor that would, or a measurable part of a gas that could influence its behavior. So let's take a look at sort of two of the kind of important laws when talking about gases. So we're going to go to the textbook now and talk a little bit about Boyles and Charles' law. So let's hide that for now. Ooh. Okay. So, talking about gas laws. Alright, so the first law we're going to talk about is Boyles' law. Ooh. Okay, Boyles' law. After the English scientist Robert Boyle. Okay, so basically this law is relating pressure and volume. And it can be explained using K and T, what we just talked about. So basically it states that P1 is times V1 is equal to P2 V2. Okay. And it's sort of saying that sort of with all other things kept constant, so we talked about the four or sort of main like attributes of gas. Well, pressure, volume, moles, and temperature. These are sort of the representative letters for them. When moles and temperature are kept constant, pressure of so the pressure times volume of sort of like one combination is equal to the pressure and volume of times volume of the other. So let's sort of go back to the textbook, the lesson plan, and sort of like look at this the infographic again. Okay, so right here we have a gas, and it looks like the temperature is kept constant at 300 Kelvin, and the number of moles, not going to individually count them, but they look to be the same. So let's look at the first volume, which seems to be, or the one on the left, it seems to be at the 4 marking, and the pressure is at 1, which I'm assuming is probably ATM or atmospheres. And in the second, on the right, it's at, the volume is at 2 and the pressure is at 2. So if this is true, then their sort of product should be the same. And so if we write this out, we have 1.0 times 4 is equal to 2 times, or I guess writing pressure first, 2.0 times 2. And they both equal 4. So that's sort of an illustration. Now, mathematically that all works out, but why does it work? Well, a gas is sort of defined as something that is freely expanding, that can expand freely into a certain amount of space. So if we think of the ideal gases, or the KMT for ideal gases, when you expand, the volume in which the moles of gas are allowed to go. Well, sorry, let me backtrack for a sec. We're going to be talking a lot about collisions, and that's what the KMT is sort of relating the most to. And we're going to take a look at how collisions are affected by this change. So let's look at them individually first. When the volume of a container increases, let's say this is container A and this is container B, and let's just say B is like about twice the size of A. Well, let's give them each 4 molecules. Alright, so what happens when you increase the volume and keep other things constant? Well, if you increase the volume here, you increase the distance between each molecule, or the average distance that the molecules have to travel before hitting each other or the wall. And therefore, collisions are going to become sort of less frequent between the molecules. And what pressure is essentially a measure of the frequency and force of collisions. So if you expand the volume, the pressure will decrease because the frequency of collisions decreases. Now if you sort of take the same thread and increase the pressure of the container, the gases will take up less volume, basically. But it's mostly sort of the causal relationship of the volume changing and the pressure changing. But this is basically just how they are related. Now let's go back to this equation that we kind of wrote for Boyles Law, and write it maybe in a different way. Well, if we have these as products right now, we can also write them as ratios. So pressure of 1 divided by V2, or I guess, yeah. But basically what we're trying to say is sort of that there can be a constant relating these two things in different scenarios. So in the textbook it also gives a very sort of simple drawing of illustration of this phenomenon, and let's just take a look at that. So, oh my goodness. Okay, so let's look at this graph. The relationship between pressure and volume is inversely proportional. If you've ever seen a graph of 1 over x, you might kind of recognize that relationship here. It's a lot easier, I think, to sort of look at this graphically. But basically what Boyles' law is trying to say is that pressure is inversely related to volume. You can sort of still see it but just based on the equation itself. Since they're product on the same side, they're going to be inversely proportional, because if one thing of the product increases, if one of the factors of the product increases, then the other factor, in order to sort of keep this constant, will have to decrease. Yeah, so basically this graph is sort of representing the equation well, it's much better drawn over there, but P1 is equal to 1 over, P1 is proportional to 1 over V1. And what do we know about proportionality? Well, they can be related by a constant. So P1 equals K over V1, basically. And that's just what this graph is. So yes, let's quickly look at Charles's law, which is relating volume and temperature. Alright, so let's sort of erase some of this for now, come back to it later. So based on what we've already talked about with temperature, it says it on the page of the textbook, but what do you guys think is the relationship between volume and temperature? Well, since sort of all of this is based on pressure as sort of talking about collisions, well, let's kind of look at the volume and pressure relationship and try to figure out what the relationship should be with temperature. So volume, like we just said, P1 is inversely related to volume. So talking about this with pressure first, it'd actually be a little bit easier. So let's take a look at these containers A and B again. And sort of, or actually let's not look at those containers. Let's just try to talk through conceptually what pressure and temperature, like what their relationship is. So if pressure is a measure of the force and frequency of collisions, temperature sort of increases both of those things, because temperature is a measure of the average kinetic energy of a gas, like the fifth sort of point of the KMT states. So when pressure increases and all other things are held constant, let's just use temperature increasing. I don't know if it's a good idea to try to draw a fire, but we're just gonna go with that. So this one's really hot, and this one's going to be a little colder. Let's use this color for ice. Maybe a little darker. Okay, so this is the cold one, and this is the hot one. And let's draw some moles of gas. Okay. So, in this hot container, what is happening? Well, since the average kinetic energy has increased, and Ke is equal to 1/2 mv squared, and therefore the velocity, or sort of like the speed of the molecules, is increased, and the Ke, the force of the molecules collisions have increased. This is going to have a much higher pressure. It's going to have a higher pressure because both the force and frequency of collisions have increased, while this colder one is going to have a lower pressure, because at a lower temperature the molecules aren't moving so fast, and therefore they're not colliding as often or as forcefully as they would be in a warmer environment, so they will have a lower pressure. Therefore, if we look back at this relationship between pressure and volume, If pressure is inversely related to volume, but sort of proportionally related to temperature, well, let's take a look at their relationship, sort of. Yeah. So at a higher temperature, there's a higher pressure, and therefore the volume will, if all things held constant, will increase, actually. Let's not confuse ourselves. Okay, so never mind. Let's just talk about this in terms of volume. So let's just use this sort of depiction again. So let's say this is a sort of expandable container, and it is able to expand based on how the gas expands. So at a higher temperature, the pressure wants to increase, but if the volume is sort of if the pressure doesn't change, if we don't allow the pressure to change, then the volume must change in place of the pressure. So if the molecules are colliding more and they're colliding faster and they're trying to increase the pressure, one way to stop the pressure from increasing is to move the molecules farther apart. So they have more distance to travel between collisions, and they won't collide as much in a larger volume. And that's how you will, even though they're moving faster and having more forceful collisions, there won't be an increase in pressure. Whereas in the second scenario, where the temperature is lower, these molecules will be moving slower and therefore colliding less frequently. In order to keep the pressure the same, you shrink the walls of the container and reduce the distance that the molecules have to travel before colliding, and that sort of keeps the pressure constant. So both of these laws sort of depend on certain things, all the other sort of factors being constant. So let's just write this relationship out. V1 over T1 is equal to V2 over T2, like it says on the book. Now I'm sorry we did not get to do practice problems today, but if you guys want to, I can put some up at the beginning of the next video. And yeah, I'll have the answers as well, sort of like I did last time. So before we go, I sort of just want to write out the sort of combined ideal gas law up on the top. So we've talked about the relationship between pressure and volume, and sort of volume and temperature and pressure and temperature in terms of kinetic molecular theory. Now there are a couple others that there's one more that we haven't really talked about too much, which is the relationship between moles and volume. Basically, if you increase a number of moles, you increase the volume, given that everything else is constant. So let's just sort of write it out all together. So the law ends up being PV equals nRT. You probably heard someone say Pivnert before, and this is probably what they were referring to. So the different parts of this, this P is pressure, V is volume. Like we said, they have an inversely proportional relationship, so they're on the same side of the equal sign. And N is the number of moles. If there's an increase in N, there's an increase in V. That's sort of like, it's called Avogadro's law because it relates moles and volume. And temperature is directly proportional to volume and pressure as well. And R is just going to be the ideal gas constant, which is, in this particular equation, 0.821, and then you have all the units. So in order to sort of keep the units canceled, there's moles on the bottom, K on the bottom to sort of accommodate moles and temperature, and then ATM on the top times L. And those are going to be the numbers on the ideal gas constant. Okay, great. So I think we'll just leave it here for today. Thanks so much for listening, and let me know if you have any further questions on this topic. We may continue to talk about this at some later time. Thank you for watching. Bye.